Good morning. I'm Dr. Derek Ho, and today I'll be explaining my work on the meta-analysis of microplastic methods, sampling, pretreatment, and analysis techniques, with a focus on fluorescence imaging via FIMAP. A little bit about me. I was originally from Singapore, where I served in the police coast guards, and there I was exposed to marine debris, and that's why I knew that I wanted to do something about it. So when I came to college in UW-Madison, where I did my bachelor's, master's, and PhD, I decided to use my skills in long exposure photography and incorporate it into my work, which you will see a lot of. I'm currently a research professor at the Academy of Natural Sciences, a postdoc at Penn, as well as a research affiliate at UW-Tacoma. Today's outline for the presentation is as follows. First, we will talk about the overview of the microplastic field, the sampling and pretreatment analysis methods, and this was all from my work in meta-analysis with Professor Masura. And I will then delve into my work on fluorescence imaging, talk about the real-world projects applying to such imaging techniques, as well as give you recommendations for your own research needs. To simplify the entire microplastic analysis methods that everybody uses right now, the most adopted method is as such. First, we sample it, we count it by using our naked eye, camera, or microscope, and then we use chemical identification such as FTIR or Raman spectroscopy, and this gives us the number of particles and the type of polymers. But this is an oversimplification of the entire field because not everybody wants this kind of information, nor do we have access to all of this instrumentation. So to break it down, for the sampling techniques, there are multiple different sampling techniques dependent on the different type of environmental matrices. That we can find microplastics in the air, in the water, and in solids, with increasing amount of turbidity and presence of other natural organic matter. For air sampling, we could either do it indoor or outdoor and get it through passive deposition, wiping it off surfaces, or through using active pumps, which sucks air through a filter and collects it on a sieve. For water samples, we could either get the surface waters, so explore microplastics in the water column, the depth, or the nephil layer, which is all the way at the bottom. Here, we will, because of how dilute all these samples are, we have to use a volume-reduced technique using nets, sieves, pumps, to reduce all the water down and to collect all the samples. We could also use bulk sampling, which typically involves using glass bottles and then sieving it sequentially through different meshes. For solids, we can find it in microplastics in bed sediments, beaches, soil runoff, and biosolids in wastewater treatment plants. And this just has different levels of turbidity, which requires different ways to collect it and treat it. But the few main techniques is selective direct extraction and pressurized fluid extraction. Additionally, you could grab samples and just digest it in its entirety to figure it out. However, that being said, the choice of these sampling methods would lead us to have different fraction sizes depending on the mesh size used, as well as the volume that we have to use sample will be dependent on how dilute the microplastic concentration is in these environmental matrices. So there is another layer that will have to be done by trial and error before we dive deeper into how the standards in which we want to use for our own personal work. Typically, 2 liters is sufficient, but people can go up to 20 liters or even hundreds of liters. For the pretreatment techniques, we tend to use 2 different ways. We'll use inorganic separation, where we use different density of salts, starting from sodium chloride all the way to heavier denser salt, sodium iodide. Some papers have done a mixture of the sequential mixtures of salts. But to summarize how it works, we hope we put in the salt and we hope the microplastics float according to its density. However, this is complicated because the density of the plastics tend to change over time and it may not be that representative. So be warned. To degrade all the natural organic matter, we can use different types of degradation solvents, acid, alkali, oxidizing agents, and enzymes. It has been found that acid and alkali tend to actually degrade the polymer integrity and will be less advised to use it. Oxidizing agents do work, except it may not have as much degradation potential as alkali. And for enzymes, is least abrasive and damaging to the polymer structure. However, it may take a very long time, or a couple of days, to do through all these different enzymes. It's slow and it's expensive. So we have to be careful with which type of pretreatment methods we use, because the type and size of the polymers will be dependent on our pretreatment methods. And be warned that the digestion solvents may affect the integrity of our plastics and vary our treatment times. As for methods of quantifying and identifying the plastics, there are multiple methods available. These are some of the methods that I have found in my method analysis. And here it's split into 4 main methods of optical imaging, spectroscopic analysis, thermal analysis, and electroanalysis. For the optical imaging, we can start off with the simplest, optical microscopes or polarized microscopes. Here, with increased magnification, we're able to just count the particles that we think is plastic. It's simple, it's cost-effective, but it tends to miss non-obvious microplastics and has a high misidentification rate of 20 to 70%. And it doesn't do too well with transparent plastics. Polarized microscopy is in the same boat. It's more subjective, and it's not too suitable for microfibers and may lead to either over or underestimation. Next, we have the higher powered microscopes, the scanning electron microscope, the transmission electron microscope, the atomic force microscope. All these are very expensive tools, but they give us high resolution, detailed surface texture morphologies, allowing us to see what happens on the surface. These methods are great for high magnification analysis. However, it may not be too good in counting the particles due to its high magnification and low field of view. Additionally, this method doesn't really offer potential for identification unless we couple it with energy dispersive X-ray spectroscopy, EDS, with SEM. However, these are very expensive methods and they can't be scaled up. The other kind of optical imaging methods is hyperspectral imaging or fluorescence imaging. Hyperspectral imaging is able to detect the spectrum across different wavelengths from UV to infrared, and these spectral information helps identify the chemical composition. However, it has low resolution due to its sensor limits, and it tends to be constrained to particles greater than 0.5 mm. For fluorescence imaging, where you dye it with stains like Nile red, it is great because it enhances the detectability of transparent particles, which often gets missed. It's adaptable to various media, and it has a potential for both quantification and identification, which I have explored. The only trouble is that this method is subject to co-staining with natural organic matter, resulting in false positives. And these vary, and the staining conditions vary, and it's a little bit more time consuming and requires optimization, which I've managed to overcome, as you'll see in a bit. For spectroscopic analysis, there are two main methods, FTIR and Raman spectroscopy, with its micro counterparts. These two methods are vibrational spectroscopic methods, and they are actually complementary in nature. FTIR absorbs in the infrared region, whereas Raman scatters light and it's within the UV-vis region. However, these methods actually do have a few shortfalls. FTIR is unable to detect particles smaller than 20 microns, a bit more time consuming because with the ATR FTIR, you have to place the particle underneath and press it down in order to get a signal. FTIR is also susceptible to water, and that may actually change the subspectral peaks. Raman spectroscopy, on the other hand, is able to go far smaller, all the way down to 1 micron. However, it is subject to interference with fluorescence. So now red stained microplastics is unable to be used with Raman spectroscopy because it blows out the spectra. For thermal methods, there are a few. Pyrolysis, thermographic analysis, TGA, thermal extraction desorption, TED, and differential scanning, colorimetry. In principle, they're all roughly this. They all work the same. Just depends on whether they have with oxygen or without, and this just decomposes the plastics and ramps it up at certain temperatures. This way, it's able to see the temperature gradient, and from that, you can then differentiate the particles. However, this method is a bit finicky because it doesn't allow us to analyze a lot of particles at the same time due to potentially interfering thermal variations. Also, the additives inside all of the plastics may convolute the spectra, causing it to require a lot to have a comparative ground truth in order to validate whether those particles are what we said it is. Oops. And for electroanalysis, these methods basically use electricity pulses to dictate the frequency of particles detected, and is able to quantify particles. However, it doesn't have very good generalizability and applicability to the larger scale of microplastic analysis due to it being limited to just quantification. So to break down what I've done in all my work, I'm in the midst of publishing a few papers. 3 of them have already been published. The last one is in prep. But as a whole, I first wrote a literature review called The Glowing Potential of Nile Red for Microplastic Identification, Science and Mechanisms of Fluorescence Imaging. Here I did a deep dive into all the aspects from choice of solvent, staining conditions, staining process, excitation, and quantification using the technology. This is a whole expose of the science and mechanisms of fluorescence imaging. So if you need a resource to understand how fluorescence imaging works, this is where you can go. Next, I worked on standardizing the choice of solvent and the staining process. This was published in Dying to Know, Harmonizing Nile Red Staining Protocols for Microplastic Identification, and I did it with Professor Masura, and this was published in June this year. Next, we incorporated multispectral imaging and machine learning. In my paper, Shedding the Light of Polymer Identity, Microplastic Detection and Identification through Nile Red Staining and Multispectral Imaging, which I'll be going into today. And lastly, we studied how the effects of weathering affects polymer surfaces, chemistry, and fluorescence response in the paper Glow and Behold. So this is now the fun part. Going to my bread and butter, which is Nile Red staining. Nile Red is a dye that binds to hydrophobic materials like lipids and plastics. Its solver chromatic properties allows it to turn fluorescent under specific wavelengths. And the fluorescence color is dependent on the properties of the plastics, which allows us to then use the physical and chemical dependent fluorescence response to differentiate the plastics. However, because of how Nile Red is in a powder, it has to be solubilized in a solvent before dispersing it onto the plastics. This multiphasic work was a little complicated, but I'm only going to give you a bit of the Spark Notes version. If you want to read, there's the link Dying to Know. But in this paper, we studied 10 different plastics, 10 of the most common plastics, and we ranked them by its polarity. So the top is polypropylene, HEP, LDPE, expanded polystyrene, ABS, polycarbonate, PVC, PET, and polyamide. Here we used 8 different solvent mixtures: hexane, chloroform, acetone, methanol, ethanol, acetone with hexane, acetone with ethanol, and acetone with water to figure out which type of solvent works best. Here we found that there was polymer degradation with quite a few of the solvents, such as hexane and chloroform. And for the fluorescence behavior was highly dependent on the functional group. Here we could see that pi-pi and non-intramolecular hydrogen bonding, such as in the chloroform and acetone, actually promotes fluorescence, whereas hydrogen bonding, methanol and ethanol, quenches the fluorescence. And we found that acetone to water, a 25% volume mix, has a strong polarity-induced fluorescence with minimal polymer degradation. And this was the solvent that we decided to stick with and use for the rest of our experiments. As I said before, natural organic matter is a bane of fluorescence imaging. However, by using Fenton oxidation, we're able to actually quench the fluorescence of wood and chitin, and even lower the fluorescence of cotton without degrading the plastics. This was found to be the case because Fenton oxidation has an iron catalyst mixed with hydrogen peroxide. This iron catalyst could bind to all these natural organic materials, effectively quenching its fluorescence. For all my samples, everything was done in glass jars, of course, and we collected 2 liters of water in duplicates for water samples. For soil and biosolids, we used about 0.5 to 1 gram of mass, and for avian stomach, we used about half the stomach, and we weighed it for normalization. For our sampling processing, we use Fenton oxidation. We didn't use any density separation, so I have to include all the fractions. And the way I circumvented that issue was quite interesting because I used an oversized filter and did everything within the filter itself. I then stained it with now red with acetone and water at 10 micrograms per ml. This is now the fun part. Now that we've gotten the fluorescent stained plastics, we can then subject it to excitation and detection with our camera. FIMAP, which stands for Fluorescence Imaging Microplastic Analysis Platform, works by exciting the plastics at 5 different wavelengths of light from 265, 310, 365, 405, and 450 nanometers, and then using 4 different optical filters and transmitting the light through. So we use green, yellow, orange, and red. Together, this allows us to explore 20 different excitation filter conditions. So after imaging all these 20 different excitation filter conditions, we can use k-means clustering to objectively select the fluorescent particles. Here we used one of the conditions, the mask 12, which is orange with 310 nanometers as a segmentation mask. This allows us to create an outline, which we then use to project across all the 20 different excitation filter conditions, and then we can collect the color data. For the color data, instead of using the typical RGB, which is in a cube-like coordinate system, we use hue, saturation, and value. That's a cylindrical coordinate. That's more intuitive. Where hue is it's on a 360-degree color wheel, and saturation goes radially outwards, and the brightness is on the z-axis down. By using it in this coordinate system, we are able to align it more similarly and more intuitively to human perception, and allow more weight to be applied onto the hue element rather than the other 2 parameters. After compiling it into the color spectral fingerprint, which is on the right, we can then use multivariate distance analysis, Mahal-Nobis distance, which then matches how these 20 different columns of data match with one another in a 3-dimensional space. And the output data will pop it out in terms of standard deviation, and values that are greater than 1 standard deviation can be easily told apart. Anything lower, not so much. Compared to other technologies, FIMAP has done very well in both the detection and identification front. It is actually outdone FIMAP, which uses 12 of the best deep learning models, but trained on subjective black and white thresholding data. Whereas for FIMAP, using our code, we are able to actually objectively detect the particles without requiring finicky thresholding, which may change with larger particles versus smaller particles, as they require different thresholds for detection. On the identification front, we outdid Myers et al., who had an 88.1% accuracy, but a misidentification between 3 different plastics. On the other hand, we performed of similar accuracy of 90% with only a misidentification between polystyrene and expanded polystyrene, which is to be expected because they are of the same chemical composition, just different densities. In the glow and behold paper, I then explored how weathering affects the fluorescence imaging. Here, we can see that as plastics degrade, there's an increase in polarity, which is like carbonyl index, and you could see a redshift in fluorescence, especially of polypropylene, LDPE, and polystyrene, where it gets red over time. Additionally, fluorescence intensity tends to lower, and some plastics will actually have different rates of oxidation. So we have to be quite wary of how we study weathered plastics. When applying Mahol-Nobis distance, there were a few outliers with Mahol-Nobis distance with lower than 1 standard deviation. However, on the most part, our code is able to actually classify most of the plastics quite accurately. Applying FIMAP to environmental samples, we used a gram of null red treated biosolids, and we were able to actually see up to 300 particles of that are bigger than 24.6 microns in length. And by augmenting the different pixel sizes, we can actually count and vary the different types of particle size studied. However, we were unable to identify the polymer species due to the limitations of the FTIR instrument and couldn't really validate our accuracy of identification. However, FIMAP, this actually goes to show that FIMAP still has a little bit more work to do because we need to do a lot of deep learning of environmental data in order to make this method more robust for environmental samples, especially at a smaller scale. So my current project involves applying FIMAP to large-scale spatial and temporal environmental monitoring with a specific focus of transport within a crete. Here we've taken weekly samples and high-resolution spatial sampling at some times. Additionally, I'm applying FIMAP to soil samples and avian stomachs to find microplastics. So because I'm a metrologist at heart, I am able to apply my instruments to multiple different environmental matrices, and I have mainly focused on surface waters, biosolids, avian stomachs, soil, and now I'm going into nanoplastics by trying to retrofit it onto microscopes. However, just because of how all these environmental matrices have different turbidity, there's a different order of pretreatment that has to be done with these samples. But we're still using phantom oxidation and now red staining. So in Philadelphia, we have Cobb's Creek, which is one of Philadelphia's last remaining surface waterways. However, it suffers from persistent trash buildup, chronic water pollution, and a lot of illegal dumping, especially from Naylor's Run. You can see that offshoot over there. I brought out a group of students to go and measure water at these 4 different locations at the same time. Here we measured the left of the transect, the right of the transect, and the middle. To treat these samples, we filtered all these 2-liter samples onto an oversized 2.5 micron filter paper and contained it in a Petri dish. That way, when we are treating it, the filter paper would contain all the plastics. We'll stain it with 15 ml of Nile red before using draining it before using phantom oxidation to then quench the natural organic material. This method can digest even the filter paper and must be done very carefully. We then image it with FIMAP and then process it with the MATLAB software. And this takes us about 2 hours in total. The results. Here we found microplastics everywhere in all 4 different locations, but in different concentrations. To orientate you on the graph, I have plotted the major axis length on the y-axis, the quantity of particles on the x-axis. For the graph trends, I have plotted the left of the transect as red and right of this transect as green, with the middle 2 being yellow. Here, comparing these 4 different groups, we can see that on the most part, the left and right tend to have more microplastics than the yellow. And this is except for group 2. And this is most probably due to the middle section in group 2 being the widest and the shallowest part of the creek, meaning that there's lower surface flow, and which means that could have more microplastics accumulated in that area. Additionally, we found that there were more microplastics on the left side of the transect than the right, and we suspect that this is due in part to the left bank being shallower than the right. So, with all of that said, I guess I just want to belabor the point that surface depth is very important because it will affect your microplastic accumulation. So please measure your depth of your area of study. Here you can see we combine all the 4 different points into one histogram, and you're able to see that there is a right skew distribution towards the smaller, most of the particles being smaller. This is worrisome because most of our detection capabilities do measure all the bigger particles, and there'll definitely be a lot more smaller particles, and these plastics will eventually degrade to nanoplastics. So here are some recommendations for your research needs. If you were to be trying to do some preliminary survey of microplastics, we found that near-infrared spectroscopy or digital holography can be employed in situ analysis to estimate whether microplastics are present. If you want to ascertain whether there's a concentration of polymers, you can use thermal analysis, particularly pyrolysis. If you need to use figure out the number of particles or the morphology, you can use optical polarized microscopy or fluorescence imaging of pre-treated samples. Additionally, if you want to study the source phase and transport, which is a little bit more time-consuming due to its large scale, you ought to use automated spectroscoping methods such as micro-FTIR or micro-Raman imaging. Hyperspectral imaging and fluorescence imaging can be used and offer potential for large-scale microplastic detection, as I've demonstrated. For weathering and degradation study, it's best to use topological, morphological data using SEM, PEM, AFM. FTIR analysis, specifically at the carbonyl and hydroxyl peaks, are valuable in determining the surface oxidation. And if you want to study absorbed contaminants with biofilms, SEM, EDS may be your best bet. But of course, there's a lot more information that we have recommended. But if you want to read out how all the different instruments that I mentioned could be used and how they are used, please tune in and check out the meta-analysis that should be coming out in about a month's time. Lastly, when you're reporting your data, please, we actually advise you to use the Kauger et al.'s checklist. He's a great guy, and he's done a lot of comprehensive work into this. But a few things to include is the materials, your QA, QC protocol, how you report your data, where you sample your these plastics at, which includes the depth, preparation techniques, identification tools used, the morphology of plastic, the quantity, the type, and to align it with data, we should try to use more standardized measures. If you want to use seeds, these seeds from 4,750 microns all the way to 38 microns and 25 microns to 1 micron for filter paper. So here's a reference to my work. The Dying to Know paper and the Shedding Light, which is machine learning papers, are open access, so feel free to use it. I've also created a tutorial of how to use it. And in the future, I do plan on doing a science Kickstarter to potentially sell these prototypes. So if you're interested, please do reach out. My contact details are in the next slide. And yeah, so if you want to follow me on Instagram or YouTube, I'm called Dr. Microplastics. You can also check out my website at plasticfreepals.org. And if you need to contact me with any questions that you may have, or if you want to collaborate, or also if you want to potentially procure a prototype, please contact me at drmicroplastics@plasticfreepals.org. Well, thank you, and I hope you have a great plastic-free day.